Assalamualaikum warahmatullahi wabarakatuh, and very good day. For this video, I would like to present to you example of solution steps for a welding problem that related to torsioner. We are going to see this problem number 1 in the lecture slide. So if you do have lecture slide with you, you may see your lecture slide and you can do the solution step with me. So firstly, we read the question. So this question says that a 20 mm thick steel bar to be used as a beam. It is welded to a vertical support by 2 fillet welds as illustrated. So which one is beam? So this is the beam. Welded to a vertical support, so this is support by 2 fillet welds. So where is the illustration for the welds? Yep, this one. So when it shows to this part, so that means it is fillet welds over here. And then because of it says for both side, so meaning they have fillet welds for both sides. So at the opposite side of on the horizontal one. So there are 2 fillet welds together that attach the beam to the support.
So question A, find the safe bending force F if the permissible shear stress in the welds is 140 megapascal. The second question is, in part A, you may find, it's already past tense, so that means you have to get the expression of F. You found a simple expression for F in terms of the allowable shear stress. So find the allowable load if the electrode is E7010, the bar is hot roll 1020, and the support is hot roll 1015.
Alright, so bear in mind we want to find bending force, but doesn't mean that the situation in the fillet welds only bending stress. Okay, in this question is actually a problem that asking us to see to evaluate the shear stress that occur in the weld part, in the weld fillet welds that happen to be primary and secondary. Okay, we'll see step by step. Alright, so the solution step, we bring inside the figure again. So this is the figure
that actually we have to solve.
Alright, in this figure we have to do the free body diagram first, so that we can evaluate to calculate where is centroid of the welds. But knowing the centroid is very important, so that we can calculate the secondary shear, especially the secondary shear stress. So firstly, I just write the weld part. This is the weld part, 2 weld parts together, the fillet welds. So the fillet welds is actually the part that attach the beam. So this is the center of the beam. Okay, beam. And then there is the force that try to bend the beam. And then given to us that this is 25, right? You just divide it by 2. And then because both fillets are exactly in the same dimension, so you just cut into 2, we get 25 mm2. So for both of them is mm. And then we know that from here to the force that try to bend the beam until the centroid, usually you name it as G or O. So let's say we put as O. Okay, so this is 150 plus half of it, so it become 175. To do a shear analysis, this is for torsional. Why, guys, it's torsional? Because if you look carefully in the slide I have presented before, whenever we do have force that try to bend the beam, but the beam has fillet like this, the shear stress that occur in the fillet weld is not bending shear stress only, is actually torsional stress. How? So the diagram is almost the same, right? So we do have force here, the centroid, meaning at the center of it, and then they have the centroid inside the well. Whenever the force that try to bend the beam, the shear stress occur in two conditions. Firstly, it just go down like bending, exactly like bending. So we'll see the stress prime. Okay, so in this scenario, the shear stress prime is in what direction? Is in y direction. And then whenever they try to go again, there is another shear stress that occur inside the filler, inside the weld, which is the secondary shear stress. So secondary shear stress is this one. So the secondary shear stress is not directly according to y and x direction. So we do have to analysis for both secondary shear stress according to the x and according to the y. So that's why in the calculation of this diagram, we have to consider both, which is the primary shear and the secondary shear, so that we can get the maximum shear stress that occur inside the fillet welds, and we compare it with the allowable shear stress as mentioned in the question. Permissible shear stress is similar with allowable shear stress. So now I bring up the diagram and then delete the unnecessary one. So we'll see how can we do the shear stress analysis together. So knowing this diagram with fillet up and down, and then we know that both of them 50, meaning dimension the B and D is 50. We know it is torsional. Then we want to know the weld properties. So where should we refer for the specific properties? Yes, we have to refer to table 9.1, which is this one. So in the table 9.1, which properties that we should use? So you see here 9.1, they say torsional properties of fillet welds. So which properties we should use? You look at the weld. The black line is the weld, and well, this one well, meaning dekat situ lah ada well. From properties class 1, class which class is related to the our diagram ataupun our problem? Yeah, this one, number 2. Why? Because if you look at number 2, I'll make it more small. If you look at number 2, yep, you just turn around, you see that the fillet is almost the same, right? And this one, right? So that's why we use property class number 2 in the torsional properties of fillet welds. Okay, I hope that's clear why we use class number 2 ataupun category 2. Shear stress analysis. We want to see so we torsional. So we write down torsional properties, table 9.1. So in the exam, should we write it down? Yeah, I think better you write it down so that we can have a proper view or can guide you to the right category. So category berapa tadi? Category 2. So in the category 2, we do have B and D. So B and D. So basically we could be both here, B and D. Both of them are 50. Okay, now we start with the primary shear. So primary shear stress, what you do, the equation is according to where? Tadi according to the y direction, right? So that's why shear prime y equal to V over A. So basically V is the shear force that occur inside the fillet weld, and A is the area of the fillet well according to the category 2. So you write it down. For the V is represented by F. So kita direct saja in welding calculation. So V could be directly represented by F, the force that try to bend, okay, over A. So for the A, 1.41 HD. Kan, ni adalah daripada kategori 2 tadi lah. This is the area. This is the location of G. Mana G tadi? Ni. And then if you calculate for moment of area, so you take that one. Okay. F over 1.41. Some textbook they use 1.414. Okay, so that is 1.41 or 14 HD. What is the H? H is the lake, or the well legs. So the well legs given in the question is 8, right? Yep, 8 mm. So 8 mm, you change it to the SI unit. So you change it to SI unit 0.008, and then the D is 50 mm, so 0.05. Okay. Then you will get 1768F kPa. So why suddenly you use kPa? Okay, so we say as the simplification of the equations already. So for the force, for the shear stress, you just directly put it as kPa. Okay, later on we'll see the comparison with the allowable shear stress. If the allowable shear stress in megapascal, then we have to make adjustment on our kPa to become megapascal. That's for primary shear stress. How about the secondary shear stress? So for the secondary shear stress, we know that it is either tau double prime according to X, and tau double prime according to the Y, and both of them is based on R. So R could be X or could be Y, and M tu adalah moment force kan, moment, and then R is the radius or the farthest distance from the centroid, R, okay, over J, can polar moment. And then definitely after knowing this, we know that we have to calculate for the J. So J is 0.707 JU, HJU. So be careful. Sometimes me myself forget about H. So H is the well legs, which is 8 mm. But we don't know JU in this equation. So you calculate for JU first. So JU is so how to get the JU? Again, it has to be from table 9.1, torsional, right? Category 2. D 3b power of 2 plus t power of 2 over 6. So what is D? What is B? D and B is from this, B and D. Okay, then you just write it down. D is 0.05, and then 3, B also 0.05 plus 0.05 of 2 over 6. Then you get the JU as 8.33, 3 power of minus 5 of the cube. In the slide I did the mistake. It shouldn't be mm. We already changed it to SI. Okay, now we get the J 0.707, H is 0.008, and the JU is 8.33.
Then we get the J as 4.713 10 power of minus 7 and power 4.
Okay, now we start with the apa nama ni, for the secondary shear. So we take the first one, tau x double prime equal to m. So for x, we have to take the dy, so because it's going down, right? It's going down. So whenever you get going down, we take y bar over j, and then mf times d, right? F times d distance, okay, and then times the y bar. Okay, I just write in full so that we can have a clear picture. So f, we don't know the f, okay. Distance, so distance is 0. What is the distance from the force to the centroid of the fillet? So yeah, definitely is 175 mm. So kena tambah lah 150 plus 25, so 0.15 plus 0.025, right? And then times the y bar. Y bar is 0.025 over the j, 4.713 times power of minus 7.
Then you get the tau x as 9.
Because b equal to d, then x bar equal to y bar, right? That means whenever you insert tau double prime for y, moment times the x bar over j. J is the same, m is the same, x is the same, meaning tau double prime y also get the same value, 9282.8 f kPa. Okay, knowing this, we can put them all together to get the total max.
So total tau max is equal to square root of tau double prime according to x direction of 2 plus primary, so in this case we only have according to the y direction, right? So primary shear stress of y plus secondary shear stress according to the y of 2. Then you fill in the value, you get the overall as 9.9282 f, sorry, 8 f power of 2, and then plus 1768 f plus 9282.8 f.
Okay, so you do have f, all of them, and all of them power of 2, you just bring out the f. So f, bring it out, then you get the value of all of them.
Then you get the total as 14413.
Sorry, 31.15 f kPa. Then it's now you have to compare the tau max that occur inside the well, compare with what? The permissible shear stress that given in the question. So since but before that, since our maximum shear stress in kPa, and since the allowable shear stress or permissible shear stress in megapascal, so our tau max need adjustment a bit, so it must be in kPa 2. So what we do, we just give them, so our tau max become what? 14.43 power of minus 3 f megapascal. Then you can relate both of them, then relate the tau all and tau max. Okay, 14.43 power of minus 3f equal to 140. Okay, then you get the f, 140 divided by 14.43. Then you get the overall as 9.7 kilonewton. Okay, this is what? This is the bending, the safe bending force in this diagram. So you just answered question A.